In this module, we're learning about segments in triangles, and we're starting with the perpendicular bisectors of a triangle. And in this particular explore activity that they're describing, there's some vocabulary that they're talking about, so make sure that you notice that when a circle contains all of the vertices of a polygon, we say that the circle is circumscribed about the polygon. So notice how in this triangle over here, the points x, y, and z are on circle C. So we say that C is the circumcircle of triangle XYZ. And the point C is the circumcenter of the triangle. So how do we find the circumcenter? In part A, they're saying that the circumcircle will pass through points P, Q, and R. So that means that the center of the circle must be equidistant from all 3 points. So here we're just talking about the points Q and R at first. And it says the center must be equidistant from Q and R. So the set of points that are equidistant from Q and R, we've talked about this before, it's the perpendicular bisector of segment QR. So use a compass and straight edge to construct that set of points. So that's what they did here. They used the compass and made this arc, and they connected the line passing through those arcs. And in part B, they're saying that the center must also be equidistant from points P and R. So they constructed the perpendicular bisector of segment PR. And in order to do that, they made this arc and this arc in order to construct the perpendicular bisector, this line. And since they intersect here, that is my circumcenter. Once I know where the center of the circle is, I can put the point of the compass at C, the center of the circle, and open it to the distance from C to P, and then just swing the arc to make the circle. So they're saying, suppose we started by constructing the set of points equidistant from P and Q, and then constructed the set of points equidistant from Q and R. In other words, would I have something different if I had done the perpendicular bisector of PQ and the perpendicular bisector of QR? Well, let's take a look. So the problem is asking me to construct the perpendicular bisector of PQ and then QR. So PQ, remember that in order to make a perpendicular bisector, I need my compass setting to be a little bit more than half of the length of PQ. And I swing my arc, and then I make the same arc from Q. I draw a line through the intersections of those arcs. And then I do the same thing for QR. So I'm making this arc from Q. I do the same compass setting from R. I draw the line connecting the intersections of those arcs. And this, therefore, is my circumcenter, and now I bring my compass to that point. I change my compass setting to be the distance from that point to one of my vertices, and here's my circumcircle. And I'm a little bit off, but If you're doing this construction on a piece of paper and you're a little bit off, similarly, don't panic. The main thing that I would be looking for when I test you on this is that you did the correct constructions. You did perpendicular bisectors. You didn't do, I don't know, angle bisectors, which maybe we have to do somewhere else. So would I ended up with the same center? Yes. Can you locate the circumcenter of a triangle without using a compass and a straight edge? And the answer is yes, and I can't physically show you in this video, but visualize taking a triangle on a piece of paper and realize that on a piece of paper that you're holding in your hand, you can find the perpendicular bisector of that segment by folding the segment so that the endpoints coincide. So you could fold this triangle so that P and Q overlap, and then that crease is your perpendicular bisector. And then you could fold the triangle again so that this time Q and R overlap. And when you open it back up, that crease will be the perpendicular bisector of segment QR. And the point at which your creases intersect is your circumcenter. More vocabulary. 3 or more lines are concurrent if they are intersecting at the same point. And we call that point of intersection the point of concurrency. So one of the things that is important to you is that all 3 perpendicular bisectors are concurrent. So notice in this diagram here how they have the point P illustrated as being the intersection of all 3 perpendicular bisectors. Since it's equidistant from the center, from the vertices, I know that PA will equal PB will equal PC. And here we're proving that. So, P is the intersection of lines L, M, and N. Since P lies on the perpendicular bisector of segment AB, then PA equals PB by the conveniently named perpendicular bisector theorem. Similarly, P lies on the perpendicular bisector again of BC. So PB will equal PC. And therefore, PA equals PB equals PC by the substitution property of equality. How could we determine whether the circumcenter of a triangle is always inside the triangle? So far, that's all we've seen. Is that all we could ever see? Let's consider. So I made this sketch in GeoGebra to show you where the circumcenter could be. So notice that in this particular triangle, it is in the triangle. Now, if I manipulate the triangle, notice how it can go outside. Notice what's interesting about the triangle, that I have this huge obtuse angle. But when the triangle is acute, it's inside. So when the triangle is acute, it's inside. When the triangle is obtuse, it's outside. Somewhere between inside and outside is on. And visually, I hope that you'd look at that triangle and say, gosh, it really looks like it's a right triangle. And if that point P is on that side, then it is a right triangle. So let's just make a note. If the triangle is acute, circumcenter is inside. If the triangle is obtuse, the circumcenter is outside. If the triangle is a right triangle, then the circumcenter is on the triangle. In this example, we're using the Circumcenter Theorem to find segment lengths in a triangle. So I am given these values. Sometimes you might find it helpful to take the information and put it in the diagram. So I know that ZM is 7. I know that ZJ is 25. And I know that HK is 20. I'm being asked to find these values. ZH and HG. Well, notice that Z is the circumcenter, and the circumcenter theorem says that it will be equidistant from the vertices of the triangle. So notice that the distance from Z to J is 25. That means that the distance from Z to H is also 25. By definition of perpendicular bisector, I know that K is the midpoint of segment GH. So if KH is 20, then KG is also 20. And when I add them together, I get that HG is 40. Similar example here. Same diagram, different values. Once again, might be helpful to write them into the diagram. ZH this time is 85, MZ is 13, HG is 136. I'm asked for KG and ZJ. So KG is this segment. We talked earlier about how K is the midpoint of segment HG. So KG will equal half of HG. So that's going to be half of 136, which is 68. Z is the circumcenter of triangle GHJ. So that means that ZG equals ZH equals ZJ. So I know that ZH is 85. So that means that ZJ is also 85. In this example, I'm told that angle ACB is a right angle. So you notice that D, the circumcenter, is on the triangle. I'm told that CD is 6.5. So what's the length of AB? Well, CD is 6.5, and CD has to equal DB, has to equal DA, since D is the circumcenter of the triangle, so this is 6.5 and this is 6.5, so that means the length of AB is 13. In this first your turn example number 5, again, I have perpendicular bisectors intersecting at a point. That point Z in this diagram is the circumcenter. I'm given information, I'm asked for information. Part number 5, let's take the information they gave us and put it in the diagram. ZG is 65, HL is 63, and ZL is 16. I'm asked for the length of HJ and ZJ. Once again, I hope that you'd realize that HJ is going to be twice the length of HL, which is 63, so this is 126. For ZJ, since ZJ is the distance from the circumcenter to a vertex, it will be the same as any other distance from the circumcenter to the vertex. So ZJ will equal ZG, which is 65. Take a moment and work through the next your turn, number 6. Now we're bringing these triangles into the coordinate plane, and we're finding the circumcenter of the triangle. So again, make sure that you're aware of the vocabulary. The circumcenter is the intersection of the perpendicular bisectors. A perpendicular bisector passes through the midpoint of a side and is perpendicular to the side. So in part A, they gave me the coordinates of a triangle, negative 6, 0, 0, 4, and 0, 0. In step 1, they graphed the triangle. In step 2, they found the equations for the two perpendicular bisectors. And here's segment RO. And notice that it is 6 units long. So halfway would be 3, which is, there's my midpoint. And since RO is a horizontal segment, I hope that you'd realize a line perpendicular to it would be a vertical line. So that's this line. Similarly, if you look at segment OS, that's 4 units long. So I could realize that half of 4 is 2. So I want to go 2 spaces into the segment. There's my midpoint of it. As I said earlier, vertical segments are perpendicular to horizontal segments. So since SO is a vertical segment, a perpendicular line to it will be this horizontal line. They intersect at this point here, so that's why negative 3, 2 is the circumcenter of the triangle. Here we're given the coordinates. Step 1, graph the triangle. Negative 1, 5 is A. B is at 5, 5. And C is 5, negative 1. Since side AB is horizontal, its perpendicular bisector will be vertical. The perpendicular bisector of segment AB is the line x equals a number, but hold on a second, let's figure out what that number is. In order to do that, I'm going to look at segment AB and count its spaces and see that it is 1, 2, 3, 4, 5, 6 spaces long. So its midpoint will be 1, 2, 3 spaces in, and the x-coordinate of that is 2. So perpendicular bisector of segment AB is the line x equals 2. Side BC is vertical. So the perpendicular bisector of it will be the horizontal line y equals a number. And again, we figure that out just by counting the spaces. So BC is 1, 2, 3, 4, 5, 6 spaces long also. Its midpoint will be 3 spaces in, so 1, 2, 3. It'll be here. And when I draw that horizontal line, it's passing through 2 on the y-axis, so it's y equals 2. The intersection of those 2 lines is this point here, 2, 2. The lines x equals 2 and y equals 2 intersect at 2, 2. Therefore, 2, 2 is the circumcenter of triangle ABC. Could a vertex of a triangle also be its circumcenter? Well, let's think about this. The vertex has to be, the circumcenter has to be equidistant from each of its vertices. So if the circumcenter is a vertex, that distance would be 0. Well, that distance would definitely not be the same as the distance from it to another vertex. Visually, this is what I'm saying. If I said that A was the circumcenter, the distance from the circumcenter to A is 0. The distance from A to C is most certainly not 0. So the answer is no, because the circumcenter must be equidistant from the vertices. Let's do one more example of finding the circumcenter of a triangle without all the vocabulary and equation stuff from the other example. Let's just look at a triangle and find its circumcenter. So first, I got to plot the triangle. So Q is at -4, 0 here. R is at 0, 0. And S is at 0, 6. Notice that segment QR is 4 units long. So its midpoint will be in the middle of 4, which is 2 units on each side. So that's here. If I draw the perpendicular bisector, that's what it would look like. Looking at segment RS, it is 6 units long, so I count 3 spaces in. 1, 2, 3, that's here. That perpendicular bisector looks like this. They intersect at -2, 3.